Okay, thanks, Pavel. So today I'm going to primarily focus on the what we have done in the Intel compiler to effectively support OpenMP SMD construct, and the several technologies we have developed inside the Intel compiler for Intel's Xeon and the Xeon Phi architecture. So under the Moore's law guidance, right, you know, the power and the performance and the power efficiency becomes one of the most important factors to driving the architecture and the programming model design. So if you look at the history of Intel's architecture, so we started for this like original start with like 2 threads, 1 core, 2 threads. The SMD weight is 128. And then we moved to the 2 core, 8 core, 12 core, 16 core, 24 core, and so on. And if you look at the vector length, we also started from 128 and up to the AVX, we went to the 256. And eventually, as of today, we got the vector length 512. So given this spectrum of the improvement of the architecture driven by the Moore's law and the performance and the power efficiency, so basically we believe the more cores, more threads, and a wider vector is the path forward for us to pushing the architecture involvement and also program model to matching the architecture design to get a performance for the end user. So that's one of the, at least one of the belief Intel has, and also we make a lot of effort pushing forward. Okay, so back to the focus of the SMD. If you look at when Intel had SSE, SSE2, SSE3, SSE3, SSE4, 4.2, AVX, AVX2, and AVX 512. If you look at the number of instructions, we increased for every generation of Intel's architecture, it increased a lot. So from like a 62 instruction up to today, we have the 3,833 instructions, vector instructions, right? So given those dramatic increase of the vector instructions, how the customer, you know, really can leverage those vector instructions to bring the best out of the hardware from the architecture to get the performance, right? That becomes one of the biggest challenges we have today because there's a CISC architecture. So this is why we come up sort of different kind of answers. Like one of the things we say, okay, let's try to standardize how the people are going to program for those SMD architecture. That's one of the driving force for Intel to propose SMD extensions into the OpenMP standard to get the next level of the parallelism beyond the multi-thread thread level parallelism. Okay. So today I'm trying to cover a few aspects we have done in the Intel's compiler. First, I show you one of the motivation why we had this. We have a showcase to show you how much you can gain really if you can fully leverage thread level parallelism and SMD level of the parallelism together. What kind of performance you could get out of the Intel's Xeon Phi architecture. Then we're going through several technologies we have put into Intel compiler. For example, function vectorization, which is beyond the original most of in the past 30 years. Once the Cree compiler first had the auto vectorization works on simple loops, right? Now we are targeting function vectorization, outer loop vectorization, and also dealing with how the vector length is less than actually your vector register, what we are going to do with that. And of course, the whole bunch of the things I'm showing you what is the fundamental issues today in order to get the vectorization done effectively, dealing with more complicated case instead of simple loops. And the set off together and the scatter optimization technology we put into the compiler and the alignment optimization for sure. It's one of the important factors. And I give you a quickly high-level summary we have done the new features with respect to OpenMP 4.0 and the 4.1. What new feature we put into the Intel's compiler, 15.0, update 3, and the 16.0 compiler. And also I'm showing you one of the case studies to show you step by step how you can get the best performance out of the architecture based on the parallelization and the vectorization. And I'll show you, talk about a little bit more about the future work. basically what is beyond the current program model we have, what we need more to fully leverage hardware future where Intel going to put into the, already put into the hardware. And of course, we try to show you what is our vision about get the performance through the program model. Okay. So let's see this simple example. This is one of the application of workload called Mandelbrot. A lot of it doing some image processing, right? If you think about that, this loop, we have this double nested loop. The outer loop is work on the image high, and the inner loop is work on the image wide. So basically, you can simply put OpenMP parallel 4 on the outer loop. So you parallelize the outer loop. And for inner loop, you put the SIMD with the safe line 32. Basically, you see, as long as you vectorize this loop with the 32, the vector length is less than 32, then it's safe to be vectorized. So basically, you see, the classical vectorization will fail because this inside for the inner loop, there's a function called this Mendel function. This is, let's say, this is an external function. When you have the function called, the compiler statically don't know anything about this function, so we don't know if this loop is legal to be vectorized or not, right? So the user, since the user wrote this application that no Mandelbrot function, even even you don't inline the compiler, when you compile the callee side, you don't know this function, but the user knows this function, what this function does. They can safely put the OMP SMD on this inner loop. So given that, so basically you parallelize the outer loop and vectorize the inner loop. But for what happens for that function call, if you just simply vectorize this loop without worry about the function, then this function, compiler basically say, oh, we don't know if this function is the vector version of this function or is just a scalar function call, right? So basically, if you vectorize this inner loop without knowing the Mandelbrot is a vector function, then basically we're calling this function 4 times or n times, basically emulate the vector execution behavior, but still vectorize this loop. And but with OpenMP extension, you see, you can declare that function as an SMD function. So once the compiler knows, because that declaration is going to be in the header file to be seen by both callee and the caller. So compiler has that information. So when compiler sees this function marked as SMD function, compiler will generate a vectorized version of this function. Then at the caller side, the compiler will replace, when we vectorize the inner loop, the X loop, the scalar function will be replaced with the vector version of the function. So if you, with all this thing is being done, what the performance speed up totally we are getting from the vectorization and the parallelization is about a 2000x speed up. So let me show you the breakdown, what this speed up comes from. Without vectorize the inner loop, just parallelize the outer loop, the maximum speed up you got with the 244 threads is about the 130. This is only 130x speed up is from the threading. So without the parallelization, only vectorize the inner loop, the speed up you got with vectorization is about 16 because Xeon Phi vector length is 512, right? The vector, if it's a single precision, then its vector length is like 16. So it's roughly got a 16x speed up. If you combine those two, basically it's 130 times 16. So that's why you got 2000x speed up. This is a showcase example. This basically tells the programmer or application engineer, say, if you can fully leverage the potential of the hardware you are having, then you can get a really good performance. Okay. Okay, since we are developing the SMD program model, instead of just look at one example, we look at a whole bunch of examples from different application domains. For example, the liberal is for one of the finance application from the bank. And the grass shader is one of the graphics application from the people like a company like a Pixel, DreamWorks, those are doing those kind of things. And L bench collision are different kind of numerical algorithm and high performance stencil code. You probably a lot of people know. So basically, if you without having this SMD explicit vector program model, you won't get those kind of speed up. By adding this pragma SMD and the SMD functions functionality, you get the average like a geomean speed up like 5. This is measured on the Intel's Core AVX2, not on the Intel's Xeon Phi. So basically, this is a sequential code with SSE 4.2 speed up because vector length is 4. With the Core AVX2, vector length becomes 8. So you get the speed up beyond the 4, right? So this basically should give you a high-level ballpark with the explicit vector program model. You can get the performance from the large set of the applications by apply the explicit SMD program model to those workloads. So let's back to, with this explicit vector program model, what are challenges? The fundamental issues today to deal with the compared to the classic or simple Livermore Lawrence, like a Livermore loop, those simple loops like a Fortran loops. One of the challenges that we are dealing today is basically when you apply this construct to this loop could be like we have an application like this simple loop could have the 1,000 lines of the code, right? Inside 1,000 lines of the code, you can have the switch statement, you can have the while loop inside, you can have the if branch inside. The control flow getting very complicated. This is way beyond the traditional auto vectorization can do. So control flow divergence is one of the challenging issues we have today. The second thing is the data divergence. The data divergence is when you have indirect memory reference. You see, once you have an indirect memory reference, not all the memory element is always in the consecutive memory, like with unit stride 1, right? It's like a of 0, of 1, of 2, of 3. It can be basically 8 elements or 4 elements can be at a completely different place. So essentially, that's why hardware has this instruction called a gather instruction. So basically, we gather the one data from here, one data from there. So basically, gather all the data. So this data divergence is also one of the challenging. So this is really the two fundamental issues we are facing today for the vectorization. So if you look at this simple loop here, basically you see you have the if branch, then you have while loop inside. So basically all those complicated control flow, and you have a function call inside, right? So how we are going to address those issues to generate the effective vector code and fully leverage the hardware, like SMD hardware support. That becomes one of the challenges for the compiler engineering team. So first one, let's see how we're going to vectorize the function. This is a very straightforward example. So let's say you have a function S4. It's a very simple scalar function. And when you mark this function as an SMD function, the compiler will generate a vector version of of that function for you. Basically, this function called the you see the argument, the return value becomes the vector type, right? So basically, essentially, your input argument from scalar becomes a vector. So basically, you can pack 4 arguments into the single vector register passed to that vector version of the function. The return value, initially you return 4 scalar value. Now you're packing those 4 return value into a single vector register and return back. So that's basically gives you idea how this original, let's say, original function call like S4 with x1, x0, 1, 2, 3. Now we packed it into the simple one single vector function call. That's called a vector function vectorization. Of course, the function body has to be generated by the compiler with the vector instructions and so on. So that's hopefully give you very high levels, idea what is a function vectorization does. Okay, so here is a very simple example to basically show you some performance benefit. Let's say you have this loop, right? This loop, then that loop has a particle velocity block function call. And this function is marked as SMD function. So simply, marking that loop, which is the outer loop, right? You marked as a SMD loop. And the function call, inside the function call, you can see there's another for loop. classical vectorization will be pretty much only vectorize the inner loop, vectorize this loop. Now we really vectorize the outer loop and also have this vector version of this function. By this simply applies the SMD program model and rely on the compiler to generate a vector code for the outer loop and a vector version of this function. You got a speed up, 2x speed up by this kind of usage of the explicit SMD program construct. Okay, so another thing is think about the function vectorization. For recursive function, if you use any other program model, for example, you use a CUDA, that probably they don't support a recursive function call because the control flow divergent, right? The architecture support. But for SMD, we were able to vectorize this recursive function. So to say this binary search function is recursively calling itself. So basically, for this function, we are going to generate the vector version. And also, when we vectorize the body of the function, the call to binary search will recursively call the vector version of that function. So this is one of the technology we build inside the Intel compiler. So far, there's no other compiler can really vectorize, recursive function. And of course, at the caller side, you basically just mark your loop. Whatever calling this function as the SMD loop will call this function vector version of this function. So this is a part of the function vectorization technology to dealing with the recursive call. So when you deal with dealing with the recursive function call, for example, those calls under the if condition, right? In order to deal with that, we basically generate two versions of this function, vector version of this function. One we call is the masked version. One is without mask. Masked version, only function calls under the condition, we need calling the masked version of that function. The masked version basically has extra argument to passing the mask into that vector function. We have the paper published, just to talk about details about the function vectorization. If you are interested, I can give you the link. You can take a look. But here, I hope I can give you a really high-level idea how this function vectorization really performs. The second technology we build in is what we call the less than 4 vectorization. So when your hardware has a small vector length, like before we have SSE2, right? The vector length is 128 bits. So after you giving a loop, after vectorization is done, your remainder loop, because all the trip count not always multiplied by 4, it's multiply of the 4 or 8. So sometimes you have a remainder loop, right? So for the remainder loop, when your original hardware vector length is small, the remainder loop, if you only have 1 or 2 iterations, the overhead is not, you just run the sequentially, that's not an issue. But once your vector length for AVX 512 or Intel Xeon Phi, the vector length becomes the 512, right? The remainder loop, after the main loop is vectorized, the remainder loop could still have enough iteration for you to do the vectorization again to apply the use a short vector, right? That's what, but those short vectors, the remainder loop is less than the full vector length, right? So that's why we call it the less than the full vector vectorization. Besides the remainder loop, of course, there sometimes in order to get the alignment correct, we have to generate the peeling loop, right? Normally, peeling loop is also short trip count loop, right? And another thing is the actual user code could have like a 3 iteration, 5 iteration loop as well in the user's code, right? So basically, less than 4 vector loop vectorization becomes one of the things we want really support to leverage the SMD hardware. So that's why for this loop, since n we don't know, basically the compiler generates the peeling loop. First loop is the peeling loop. You peel a few iterations, you get alignment done right. Then in the loop in the middle, this middle is your main vector loop. Vectorizes, this is we vectorized for Xeon Phi, so that's why it's 512 bits, right? And there's a remainder loop. Before, the remainder loop is only executed sequentially. The peeling loop and the remainder loop was both are executed sequentially, right? Now, what we want to do, we also want to vectorize this loop and also vectorize this loop. So that's what called a vectorization of the less than 4 vector vectorization. So on the Intel Xeon Phi architecture, you know, we have this masking technology introduced. That's the first architecture really have the masks, what we call the masking architecture, right? So essentially, you can, for the peeling loop, we can generate the, you know, using the mask because the total number of the iteration is less than your 4 vector, right? So only length which is less than, we need to mask them out. That's what we need to use the masking. And put the mask on this operation, the FMA and so on. So basically you can mask. Though actually if the mask is less than 16, this is actually, eventually we can get rid of this loop, just have those 2 instructions. So same thing for the remainder loop. We're also using same masking technology. If eventually if the n, let's say if the n is between the main trip count to n is less than 16, then actually this this loop is we can get rid of this loop, essentially just like 3 instructions. So that's what we call the re-vectorize the the peeling loop and the remainder loop. We have a number of performance data to show that vectorize this one give you more, like average can give you extra like 20% performance gain or 30% performance gain by re-vectorize the short trip count loop. Okay. So another technology, as I mentioned before, is basically how to deal with the predication and the masking for the dealing with the conditional and the while loop, right? So giving this very simple example, you say you have a loop marked as SIMD loop, and you have this if condition. So this is before the vectorizer, right? So how we are going to vectorize this one? One of the things we do is if you have a mask architecture support. So basically you compute your mask, put into the vector, this M is a vector mask, right? Then for every mask, you sort of treated them as a predicate. So basically you sort of mask the execution for every element through the hardware. So that's how you're dealing with this masking, you know, condition when you mask, vectorize this loop with masking. And here is another way. So basically for every, for else branch, you get a negative M, right? So it's reverse. So for the true branch, you just get M. That's how you flat the control flow becomes, this is called a predicate-based the control flow flatten. So with this, you can vectorize with all those complicated control flow. Of course, if you have nested if, the computation of the mask is going to become more complicated. But the compiler was able to, pretty much the compiler, we are able to deal with those complicated control flow. Another thing is if your architecture don't have the support of the masking support, this masking support, then you can use a blend. But for the blending, you have to approve it is safe to do that. Otherwise, it's not safe to do. Then you have to serialize your control flow, right? So once you prove it's safe to do blending, so basically you say for the true branch, right? The true branch you just end with your mask, and your else branch you bit end with your negative mask. So it's reversed, right? So then you do the blending, which is all. Then you get the result. This is only can be done if you know those memory, load and store can be done before actually under the condition. That's what we call the safety need to be approved. But sometimes the compiler can do the what we call the speculative memory load and store. Under certain options, let the user to control if you want to generate the blended code, or you really use the masking the code. Because this one is, in certain cases, this one is more efficient than uses the masked technology, right? So basically, we provide options for the user to provide the control whenever the compiler is not able to safely prove the blending is safe, but still user want to get the same level of the performance as you apply the blending. So that's one of the things we have done in the compiler. Okay. So basically, if you look at all those architecture involvement, so we started with SSE, SSE2. At that time, we don't have this architecture doesn't have the hardware, doesn't have the masking support. So essentially, we have to emulate the masking behavior through by the serialized code, or or use a blending. The AVX is the first architecture we introduced. We masked the move, basically memory load and store. But this is still not power efficient enough because it's the first generation with to support masking. Then we had this masked gather introduced in the AVX2. I will show you some gather optimization later. And the Intel's mic architecture was the first architecture has a truly masking support. Of course, latest AVX 512 KNL is adding more efficient masking architecture better than Mac. Whereas basically the masking normally come with the overhead. Even hardware, you have hardware support, it always has the overhead. So now the hardware team is trying to reduce the overhead of the masking, all the instructions with mask. Okay. In the next generation of the Intel's Xeon Phi. So we talk about a little bit of the gather optimization. Here is a simple example to show you how we can, fully reduce the gather overhead. If you look at this simple loop, this loop is one of the typical loops without pragma OMP SMD. The compiler couldn't figure out this loop is a vectorizable loop because there's indirect, you say II is the subscript of the U underscore D and the temp underscore data, right? Because this II, we don't know the value of the A underscore diag underscore J. Because this value, if this value for the different J, if you have the same I, then you have the conflict, right? You have the, you will have some conflict. So basically, giving those aliasing or those kinds of things, compiler may not be able to figure out if there's a conflict between the write to those results and the load to this indirect referencing. So the pragma, since the user say, oh, you are not going to write any memory to have a conflict with the load of the U underscore D and the temp underscore data. So basically, they can put the pragma SMD here. Then compiler, okay, say we know, okay, the user asserts this loop is safe to be vectorized, even you have indirect memory reference. So given that, but the issue is, okay, the compiler generates the code, it can vectorize this loop, get it vectorized, but since you have I, we don't know I from each J, right? I is in the consecutive memory. It gives you a consecutive, I is linear or not. So basically, we end up generate a gather for the U underscore data and also generate another gather for temp underscore data. So basically, you gather from the one guy here, the second guy here, a third guy here. So it's come from different location, right? So we generate a gather instruction for that. So with the gather instruction, the naive implementation, we will generate two gather instructions, one gather for this, one gather for this. Then two FMA, this is the FMA instruction, right? That's the naive implementation. But the smart implementation you could do, what we could do is we can load the address, generate this address computation under the, create the temporary address, load the address of this, where it is, yeah, address of U and the data and the address of into the temporary address, right? So this load is just loading the address with a different, with the same J. So it's okay, we generate basically the address load. But after we generate this one, you can see we can, actual computation is moved host outside the if branch. Then you basically generate a single, you just can generate one gather and one FMA. So this is going to be So with this code sequence, the vector code we generate is much more efficient than 2 gather and 1 FMA. So this is one of the gather optimization. Either compiler could do, or even the programmer can do themselves by reduce the gather and FMA usage. Okay. So another gather optimization is basically you can say, yeah, this simple loop, user say, okay, well, go ahead and vectorize this loop. But if you look at the load of the day of the 5 times j, because it's, you see the stride is not in the same consecutive memory, right? The stride is 5. So the first element for this one, the green one, is here. The second element is here. The third element is here. So basically, we have to generate the gather, to gather all the data. So essentially, for those 3 of them, we generate 3 gather, the green, blue, and brown, right? So we have the 3 gather instruction. So now, if the compiler with this same code sequence compiler, we have to, what we did is we try to do what we call adjacent gather and scatter optimization. We know, those are always a constant, those are stride is always 5. So we just load this 4 element, load this 4 element, then do the shuffle. Then to shuffle, 5 times, you get all the data green together and all the blue together and all the brown together. So basically, for this adjacent gather and scatter optimization, we were able to get rid of all the gather instructions by just use unit stride vector load instruction and doing the shuffle to get all the data into the consecutive memory. Then when you do the computation, you can just do the vector add, vector multiply. So basically you can, this is even you have this shuffle overhead by shuffling this green to here, right? Shuffle this green to the here. The shuffle overhead is still much lower than the gather overhead. So the question. This one?
I wonder if I would be able to.
Oh, this one I didn't show the whole function because there's an Aliasing issue. The L of the data, this read and this could Alice all those kind of, and return that whole bunch of code later on. Yeah. Compiler could do that, but the only way the compiler do that is generate a multi-version code to do the runtime dependence test, right? Then that comes down to the runtime dependence test overhead and also the code size issue, right? So this is a trade-off between and also for the runtime dependence, we do a lot for auto vectorization. We do a lot of the runtime test. But sometimes this runtime test actually kills the performance in the, probably already offset the benefit you got from vectorization. Quite sometimes we say that. Okay. Any question on this slide? Good. Okay. All right. So this is a slide for whoever worked on the Intel Xeon Phi performance tuning. Because if you look at the hardware specification, there's a number of pages talking about the alignment, the special requirement for the microarchitecture. So I summarized this as a single slide. That's pretty much, I think, all you need to know. Even if you don't remember it, later on you just look at this single slide, you know what you need to do for when you're tuning the performance for Intel's Xeon Phi. So for Xeon Phi, basically there's no because for the Intel Xeon Phi, if you use the vector instruction for the simple vector load and the store, it always requires you to require the data is 64-byte aligned to get the performance, best performance. That's the first requirement. And any SIMD instruction on the Intel Xeon Phi require at minimum, at least requires element-wise the alignment. Otherwise, there's a faulting error. I will talk about what is a faulting. Okay, so misaligned. So basically, if you data is not element-wise aligned, when you use the vector load and store, you will get a faulting error. Basically, you get segmentation fault. So there's a way to for you to to avoid the faulting error, but with the performance penalty. And on the Intel's Xeon Phi architecture, as you know, different than Xeon. On the Xeon, whoever used the SSE 4.2, SSE 4, we have this move APS for aligned data access. And also you have the move UPS for the unaligned data access, right? But for mic architecture, there is no instruction called vmove UPS. But this instruction was added to the AVX 512. But at that time, for Intel's Xeon Phi, the mic architecture, we don't have that. So in order to do that, we basically we have to use the unpacked low and unpacked high to handle the unaligned data access. So that's one of the things you need to pay attention. But there's a caveat for using unpacked low and high instruction for the unaligned memory load and store is once you memory access across the patch boundary, if you use those instructions, you get a faulting error, except if you use the mask the gather and the scatter. That's one of the special requirements for the mic architecture. So that's pretty much a 4 bullet you need to remember, or later on you can look for when you work on the Intel Xeon Phi performance tuning. But given those requirements we have on the Intel's mic architecture, so basically for the compiler we do, because alignment really is one of the key issues, key factors, getting factor for you getting the performance. So compiler does very aggressive the peeling and optimization for the when you vectorize on the Intel's Xeon Phi architecture, mic architecture. And basically also we provide for the unmasked, unaligned and the vector load and store, compiler try to use unpacking load and packed store instructions, right? So as long as if for unmasked, but for unaligned masked load and store, so basically we have to use, for safety reason, although we know there's a big performance penalty, we have to use the gather and the scatter instructions. That's what pretty much the compiler's guidelines to generate the code. And besides that, we added one option for provide the user to do the padding. So as you remember before, I said once you use the certain unpacked low and high unpacked load and the packed store instruction, right? Load and store instruction. If you cross your page boundary, even you use the data is masked out, you still get a faulting error. So that's unless you use a gather and a scatter. But in order to avoid to use gather and scatter instruction, and we allow user to do the padding. So basically, you're padding the 64 bytes added to your original memory allocation to guarantee your memory access never going to run out of the 64 bytes, right? So in that case, with this option on, you can always, the compiler, so give the compiler the safety to always generate the unpacked and packing and the packing load and the store instruction, so we don't need to generate a gather and the scatter instruction. So I have an example to show you how it works. So that's pretty much whoever use Intel mic architecture, that's the alignment requirement and what compiler does to get a safe alignment and also getting the performance. That's pretty much 8 bullets you need to remember instead of reading pages of the spec. Okay. Okay, here's a very simple example. You don't need to read all those assembly. I can just highlight what is the issue there. So without to do this safe padding option I mentioned before, you see, for safety reason, the compiler, this is a simple loop, right? Doing from this simple array element plus and multi FMA operations, right? So since we don't know the size of the n, so the compiler, so basically compiler have to generate, mask together. This is K radius masking, K is masking. we just, as I mentioned before, for safety reason, because we don't want to get a segmentation fault, right? The compiler has to generate a gather instruction. So this gather instruction is generated is not because you load the data from different location. In this case, we know data is the same location, but we don't know if it's safe for the last iteration to load those data, right? That's why we generate the mask, the gather, and the scatter instruction, because this is the only safety guarantee we have from hardware. So now, if you change your code a little bit at your caller side, then you're packing whatever original size plus 64-bit, right? So basically, you guarantee the last vector instruction not cross a page boundary. That's the guarantee we can have by just simply adding the 64, because the vector length is always less than 64, right? So in that case, you can see we can get rid of all those gather instructions, generate unpacked, low and high, low and unpacked high instruction. This gives a huge performance boost than this piece of the code. So that's an example showing you with this simple, approach, you can get much better performance on the Intel Xeon Phi architecture. Any questions on this slide? You don't need to read the assembly in detail. So basically, this highlight why we provide that option for you to, use the unpacked load and store instruction to deal with unaligned data access. Okay. So far, any questions with all those technologies I presented? Good. All right. So Intel compiler, $15 compiler and $16 compiler, we started support. We had added the implementation for, with respect to SMD extensions. So all those SMD extensions in the 4.0 and the 4.1 specification of the OpenMP is implemented inside Intel's $15 and the $16 compiler. So of course, the main feature is SMD, right? And also those combined construct SMD with parallel target, all those also supported. And this is not part of the OpenMP language spec. I will show you what this feature means, called user-defined vector variant function. There was another extension in the OpenMP 4.1. It's called on the ordered construct. We added a qualifier called SMD, right? So this is one of the, since in one of the previous talk, one attendee asked why we need a SMD construct, because for auto-vectorization, once you have the big loop, and inside the big loop, there's a portion of the code actually is not vectorizable. The auto-vectorizer basically bails out. So since this is a loop, it's not a vectorizable loop, right? But with this explicit vector program model, it's like a parallel. For parallel for loop, you can put all of the construct inside your parallel loop to guarantee partial of your code follow obey certain order required by you. This is the same thing for the SMD loop. We have the huge customer application. The loop is about 1,000 lines of the code, but there's a portion of the loop inside the loop actually has the loop carried backward dependence, which prevents the auto-vectorization. But for that piece of the code, you can put it into the ordered construct, right? The compiler will honor the ordering, required by user. The rest of the code after the loop can still be vectorized. Then we give the huge performance boost for the customer's code without them to sort of split this huge loop or figure out a different way to split the loop for the sequential part, SMD part, or parallel part. Simply put in the pragma SMD, OMP SMD on that loop and put this ordered construct into that surrounded that portion of the sequential code. Then the entire loop still gets vectorized and the required ordering still happens for that loop. So that's one of the examples to show you why we're promoting the explicit SMD program model. Any questions on this slide? The rest of the blue part is related to the threading part. the threading, like accelerator support, new thread affinity support, error handling like cancellation construct, and the sequentially consistent atomics. Basically, we have CS underscore SQ for the atomic construct. All those is supported in our 15.0 and 16.0 compiler. This is more like a summary, you know, which feature is available in the which compiler. Okay. All right. So let's back to the user-defined vector variant function. So in the OpenMP standard, we had this declare SMD construct for the user to mark the scalar function as SMD function, let the compiler to generate a vector version for it, right? So now we got some customer feedback say, oh, I'm not really sure the compiler can generate the most optimized vector version of the function, which I expect, the customer expect. So basically say, okay, we can provide you the vector version of that function. The question is how you can, you know, compiler can associate this user provide the vector version of the function with that scalar function in the original at the caller side, which user calls in the sequential code, right? So that's the feature. Basically say the user provides the manually written, if you use an inline assembly vector, use vector instructions, or use vector intrinsics to write your own version of the vector function. But you need to annotate this function. Say, this is a function implemented. I want the compiler to replace, when you vectorize the caller, replace your scalar function with my vector version of the function. That's the request from the user. So basically, again, this is the original scalar function. A user implemented their vector version of the function. How the compiler can associate those two functions together. When we vectorize the function, whatever the loop, so calling this scalar one, when we vectorize this loop, then we can replace this mymax with the user provide my vext vec, right? That's pretty much the scenario of this feature. So now we provide because this is not part of OpenMP standard yet. So what we did, we added this decal spec for this is a Windows syntax. This is a Linux syntax. Basically, user says, oh, this vector variant function, this vector function implements this scalar function is for this scalar function. Of course, there's a whole bunch of clauses for that, right? Those clauses basically when you do when you replace a scalar function to the vector function, there's a signature match, and a whole bunch of technology needs to happen to get the right vector version for it. So basically, that's pretty much a syntax for the associate the user provide the vector variant function to mapping back to the original scalar function. Okay, so basically we introduced the two things. One is called the vector variant, then there's a clause called the implement, right? Okay, so if you look at that one, then what the user in the code they can do. So basically this is my original scalar function. User can still mark this function as a vector function, and the compiler will generate a vector version for it. And the user also writes their own vector variant function, right? That says this vector variant implements this my max, right? So if the compiler the compiler will generate a vector version, but since the user also provided their own vector variant, we normally the way we did the compiler more trust the user. You know, the compiler when we do the vectorization on the caller side, we will replace the scalar function with the user-defined vector function, over which we are not taking the compiler generated vector version. So we trust the user say you are smart. That's the way you can read that. Okay, so basically that's pretty much the high-level idea of this new vector variant function beyond the current OpenMP specification. Any questions on this? Hopefully this example is simple enough for you guys to understand. Okay. So basically that's what I already mentioned. The selecting rule is when the compiler has two versions of the vector function. One is user defined, when the compiler generates the compiler pick up the user-defined one over the compiler generated one. We trust the programmer more. Of course, if the programmer didn't, the version they provided, if it's not good as the compiler generated one, the user can always remove this one, right? If they don't get the performance, if they think their code, the vector version they have is not good as the compiler generated, they can always remove that. All right, so hope that's. This is a usage example. I'm not going through it again. This is basically how to, shows you how to this causes to mark this so the compiler can do the right signature match to get the right version, generated to use this feature. Okay. And as we say, there's another extension we put into the because if you look at OpenMP specs, they don't have the process clause, but for Intel, we got a request from customer. They want to control the process, the code, the compiler can generate for different architecture. So we added the process clause with all kinds of names. So basically, in the declare SMD, if you add a process with for example, call fourth generation GenAVX, so we will use this instruction set to generate a vectorized code. So this is Intel's extension based on the customer request for Intel architecture. All right, let's quickly go through a quick the case study. So for this case study, so basically this embody parallelization and vectorization study. So if you look at the original code, so basically you parallelize outer loop, vectorize the inner loop, and the actual code the user has actually they did the strip mining. So you actually parallelization happens in the middle loop, and the vectorization applies to the innermost loop. The outer loop just goes through the chunk, right? Each chunk. So this is the code we are dealing with for the case study. So if you look at this one, so basically you have 3 loops, 1, 2, 3. This is a chunk, go through each chunk. This is for each element for the outer, right? This is for the inner. With after stream mining, it's done. So if you, for this simple loop, 3 level nested loop, so what you could do, as I mentioned before, you parallelize the middle loop, and you got some speed up, 17.3 speed up on the on the Xeon Phi. You see the Xeon, because each core of the KNC is slower than the Xeon, like a Haswell, right? So next one, you will apply the vectorization for the inner loop. So basically, you apply your vectorization in the inner loop. Then you host the speed up. You got down to the 4 from the 20 seconds plus second, it becomes the 4 seconds. And for KNC, you can see you got a 16-way vector instruction. Now it's faster than the Haswell system now. It's down to the 2.5x. So basically, this is another example to show you if you can fully leverage parallelization and SMD vectorization, you can really get the good performance on the given hardware. Okay. So besides that, there's a more fine-grained tuning. If you think about the step-by-step parallelization, vectorization, and the vectorization for the tuning, right? So now you're adding all those alignment clauses on it. So the compiler, instead of using unpack the low and the high instruction, now we can really use a vector move APS instruction, which is much faster. You can see you got for the Xeon, you don't get that much gain because we have that vector move UPS online the load store instruction, simple online the load store instruction. The performance is very close to aligned one. But on the Xeon Phi, for KNC, you can see you get with alignment improvement, you got about 12% improvement by using the aligned load and the stores. Okay. The next thing is the further one is how you can, for certain customers, if you don't really need 16 bits the precision, right? For certain application, you say, oh, I'm only the 12-bit precision is good enough for me for my application. You can lower your precision, your accuracy requirement, then getting much better performs. You can see with this tuning, basically the KNC performance becomes just about 1 second. So that's all the step-by-step performance tuning you can get to get, to get the best performance. So this is basically the recap all the performance gain you get with different optimizations. Okay, now back to now. This is a picture I always try to show people. For a lot of people, as long as they get a vectorization okay, they got a certain performance, they're probably happy with that. But there is a certain set of the people that have a different mindset or mentality. Those scientists in the national lab, they say even if they get a certain performance, they didn't meet their expectation. They probably ask you why. So basically, once you see the SMD loop is vectorized, as I mentioned before, it's just the beginning. There's still more you could do to to improve the performance by like what we did, the gather optimization, to the alignment optimization, and the accuracy control to improve the performance. Okay. So in order to do that, Intel will build a set of tools to give you detailed report talking about the vectorization quality. So to help the programmer to tuning and fine-tune and improve the performance. So this is a set of the tools we provide conjunction with compiler's work. So if you're interested, we can talk a little bit more offline. And finally, the future work. So in the 4.1 specification, we're adding more features. But in the future, there's a lot more stuff we could do to support a function point vectorization, virtual function vectorization, to deal with the loops and the function with actually has a data conflict. We have the whole set of the new hardware features we are working on, and we have to implement them in the compiler, like a V-conflict, V-compress, V-expand, and the search loop vectorization, array of the structure of array converting, and so how to deal with the exception handling for C++ code inside the SMD loop. So there's a long way for us to really satisfy our customer with a lot of new features. In the future, we can work on to add to the OpenMP in the compiler. All right, this is an example to show you how this, this loop actually is not a vectorizable loop because this conditional increment of the index. This is how loop carry the backward dependence. But with V-expand instruction, V-compress instruction, we were able to vectorize this kind of loop. We need to extend our language program model to support to vectorize those kind of the loop with, actually loop carry the dependence, right? All right, so final summary. The reality is there's no single solution. We have all kinds of model to provide you, to make your customer happy. There's no free lunch for sure. You have to deal working with the compiler, work with the program model, and work with the hardware to get the performance. And there's so many program models emerging, but based on our experience, the increment approach applying the learning, all the stuff we have done in the compiler, we proposed to the OpenMP language extension, and is based on learning from HPC and the graphics application. And general, our guiding principle is to try to make sure the language extension is simple and portable across all those CPU, core processor, and the GPU. That's our guiding principle to having for the future language extension and the program model extension. That's pretty much I have of the day. Any questions? I can take a couple of.
We have time for one or two short questions.
Yeah. Go ahead.
Yeah, so within the SIMD kernel, what do you think about possibilities to have communication across the different lanes?
Yes, that's exactly this one. The V conflict, you see, the V conflict instruction we introduced, the one you have a conflict between the, across the lane. So we actually, besides this one, and also the V conflict, so that's the way. The current SMD construct don't have we see all that has to be safe, no cross-lane operations, right? So that we probably need to add one more actual clause to the SMD construct. Say we allow conflict, then let the compiler to use the V-conflict instruction to deal with the cross-link communication. Yeah, that's exactly the future extension we can add it to the OpenMP construct. Yeah, that's actually the direction we are working on. Any other questions? All right, good. Thanks.